Share screen. Okay, so let's go through question 10 now. Did anyone manage to get this? I think Rihanna got it from what I interpreted from messages, but did anyone else? Okay, let's go. Noah. Okay, let's go through it together. So a couple of you thought that this, along with question 8, were the hardest ones. Yeah, I think that you're right. It does feel like a load of bash. It's a lot of case checking. And I think that with this one, the trick is just to figure out how to systematically go through all the possibilities and make it faster for yourself. Because, I mean, while question 8 required some ingenuity, like figuring out that it would become easier if you made the triangle right angled, this one, like there's no trick you can do. You sort of have to, in some way or another, check all the possibilities to know which ones are compatible. Anyway, I think maybe the first step will be to read the question. Okay, so a pair of positive integers is called compatible if one of the numbers equals the sum of all the digits and the other number equals the product of all the digits. Okay, so I'm just going to write this out as a pair AB, where A and B are integers. And I'm going to say that A is the sum. Okay, so sum of digits, and B is equal to the product of all the digits, just to keep track. Okay, and I need them to be positive, less than 100, and I need them to be less than 100. So we're trying to look for all of the pairs of compatible numbers of this form that have these constraints. Yeah, so I think, sorry, what digits? Oh, okay. So for those of you who haven't seen this before, this is sigma notation. So this is a capital sigma. Sigma is a Greek letter, and it's usually used to denote sums. And this is capital pi, which is usually used to denote products. And I was lazy, so I decided to use symbols there so that I don't have to write it out every time. This is an abuse of notation. I'm just sort of using the symbols to remind myself what everything means. Okay. Yeah, okay. So I wanted to say that, like, basically we've got essentially like 100 by 100 possible pairs, right? There are 100 by 100 pairs of numbers A, B under these restrictions. So they're between 0 and 100. They're integers. Okay, not 100, it's 99. Close enough. 99, 99. So I've basically got to check all the numbers, and I've got to check whether a given pair of numbers, say 7 and 18, I need to check the possibility where 18 is the product and 7 is the sum of digits, or where 7 is the product and 18 is the sum of digits. So it already feels very difficult because there's just so much to check. And we have absolutely no idea how many pairs are going to work out. Okay, so I like Anson's thinking. Oh, you just do it 100 times, you just bash it out 100 times. But yeah, I mean, I guess that's essentially the approach. We have to actually check all of these. in order to be sure of our answer, to know that we've realized why certain pairs don't work and why certain pairs do work. And it's difficult to begin with because you don't even know how many pairs are going to be compatible in the end. Like, I have no idea if like 30% of these pairs are going to be compatible, or whether it's just 2% or even less than that. So yeah, it's already really difficult. And I think, I mean, this is always the case. This is usually the case, but especially for this reason, it's really good to just feel around first by looking at small examples and just get a feel for the question and try and find patterns or things that are happening that we can exploit, and then make our system of checking all these pairs way faster. Definitely under the category of skip at first sight. Okay, so I'm going to take you all through like just how I'm going to take you all through like some small examples and what we can figure out from those examples. If you look at the AMT solutions, like keep in mind that those solutions have been heavily refined and they don't exactly take you through small examples to understand the question. And so if you're going to learn how to do questions by looking at the AMT solutions, then I guess what I'm saying is you would have to first attempt the problem in order to even understand like why the solution is what it is and why they decided to break it down into certain cases or whatever. Yeah, so anyway, let's just go through this process together and actually just do some small examples together and see what we can figure out from those examples and what we can do next. Okay, so the first kind of example I wanted to start with was just the really small ones. And I think that a nice definition of small is if one of those numbers is actually 1. Okay, so I'm going to use curly braces just to emphasize that I don't know if 1 is the product or if it's the sum of digits. So let's just have a think about what this could be. So, okay, we're thinking about 1. So let's see. So let's suppose that 1 is the product of digits. See, this is why I wanted symbols, so that I don't have to write product every single time. Okay, so if 1 is the product of digits and all the digits are integers, then that means that all the digits have to be 1. All the digits in this pair have to be 1. Okay, and so that means for this, I have 2 choices. It can either be 1 or it can be 11, because those are the ones that are positive and less than, oh yeah, I could have written 1 equals b, but just so that we can follow along and not get lost in what every pronumeral means, I'm just going to write it out. But of course, if you're by yourself, that's the best thing. You can use whatever notation you want and you'll understand it because you're the one who made it up. Okay, so 1 or 11. But if 1 is the product, then that means the other number has to be the sum of digits. But 1 is not equal to the sum of digits, which is 1 plus 1, which is 2. And 11 is also not equal to 3, which is the sum of digits. And so that doesn't work. So that means that 1 has to be the sum of digits, okay? Because it's not the product, since that didn't work. Okay, but then if it's the sum of digits, then that means that the second number has to be 0. But that's not allowed because our integers have to be positive. So this just doesn't work. And we take away from this that 1 is not in any compatible pair. I'm going to call that a CP for short. Okay. So that's a good start. That already eliminates 99 pairs. And I think that you might realize that maybe something similar will happen if I just generalize this to any single digit number. So if I have a single digit number A0 and something here, let's see what happens. Because the idea with our one was that, I don't know, it was just too small and too restricted. And I think what I drew from is this sum of digits not working out because this thing is forced to be 0. And that sort of leads you to think maybe single digits will have this phenomenon because, okay, I mean, let's just check it out, right? So let's first suppose that A0 is the sum of digits because that is what inspired this generalization. So if it's the sum of digits, then that means that this has to be 0 because the sum of digits is going to be A0 plus the digits in here in the second number. And so that forces the digits in the second number to be 0. So it's the exact same thing happening. That can't work. And so A0 can't be the sum of digits. And so the question is, can A0, a single digit number, be the product? So if A0 is the product of digits, let's see what happens. Okay, if A0 was the product, then A0 would have to be A0 times the product of digits in this second number, which forces the digits in this second number to be either 1 or 11. So you see the same thing happening. Okay, so let's consider each case. So let's see if we had 1 and A0, where 1 is the sum and A0 is the product. Okay, so if 1 was the sum, then this would force A0 to be 0 because 1 is already counting itself. Oh, actually, sorry, we didn't even have to check this. Let's not even, we didn't have to check this because we already established that 1 is not in any compatible pair. So no need to check it. Now let's just check the 11 case. Okay, so if we've got 11 and A0, then 11 is equal to the sum of digits. But then the 11 itself already contributes a digit sum of 2. And that means that the rest of the digits have to add up to 9. So that 11 is equal to 2 plus 9. Okay. But then A0 is a single digit number from what I began with. And so that means that A0 itself has to be 9. Okay, so let's see if that works. Let's just check. 11 and 9, does it work? So is 11 equal to the sum of digits? 1 plus 1 plus 9? Yes. Is 9 equal to the product of digits? Yes. Yay, so we found one compatible pair. This is a CP, which feels good for now. Okay, so yeah, we've already eliminated anything with ones. And not only did we find a compatible pair, we found that any single digit cannot be in a CP unless it is 11 and 9. Because this analysis basically forced A0 to be 9. Okay, so we've already eliminated a lot of possibilities. And now my thinking is, I mean, we went from 1 and recognized this thing here with the digit sum. And we sort of generalized by realizing that the digit sum can't be too small. It can't be too small. And so we thought about just single digit numbers. And again, it's too small to be the digit sum. But then by contrast, like this wouldn't happen if we had 17 as the digit sum, right? Because 17 contributes a total digit sum of 8, which leaves 9 digit sum for the other number. And that is achievable. Like it doesn't force the other number to be 0. So I think this observation sort of pushes us to see why that's the case and explore this further and like formalize this. Okay, what's happening in the chat? Okay, so by contrast, yeah, this thing happens and that leads us to want to formalize what's going on and understand it better. So remember we've got A and B where A was the digit sum and B was the product. So the reason that this thing works here is because what we have is if we write the numbers as A1, A0 and B1, B0, where these are digits, and I'm looking at 2-digit numbers because I've already considered all of my 1-digit number cases. I've already like exhausted all possibilities except for 9 and 11. So 2-digit numbers, then if I convert this into compatible pair restrictions, then I've got that the number A1, A0, which I can write as 10A1 plus A0 is equal to the digit sum, which is A0 plus A1 plus B0 plus B1. And also the other number, which I can write like this, is the product. Okay. So let's look at this a little further. This turns into, by cancelling these and subtracting A1 from both sides, 9A1 is equal to B0 plus B1. And I think that's interesting because before we were thinking that the sum number can't be too small, right? And now we realize something. We realize that B0 and B1 are digits. These are single digits. So that means that this sum is less than or equal to 9 plus 9, which is 18. And so that means 9A1 is less than or equal to 18. That forces A1 to be less than or equal to 2. And so that means that A can't be too big either. I think that's another significant accomplishment because this again reduces our sample space even more. Okay. So I'm going to go back up to the top. Let's just do some other simple cases. Just another quick observation you can make is that if you have any digit equal to 0, then the product would be 0. But none of the numbers can be 0. So that means no digits are 0. Okay. So I think it might be good to just do a little more examples now because we've reduced our sample space quite a lot and we understand the sum pretty well, but we don't know what we can think about the product just yet exactly. So let's just start with a simple example. I've already found 11,9. And I guess I could try and determine whether there are any other pairs that would work. So let's have a look. I mean, I could try and figure out if there are any other 2-digit pairs that would work, because again, I've already gone through all the 1-digit pairs. Okay, so, well, if 11 was the product, well, 11 can only be broken down into 1 times 11 because it's prime. But that doesn't allow 11 to be the product of digits. So we can't have that. So we're already starting to see restrictions on products. Like, for example, the product can't be prime. Unless, or it can be prime, like if we have a case where it's like 119, like this case, but prime is typically bad. Anyway, okay, so that means 11 has to be the sum of digits. But then that forces the digit sum of the other pair to be 9. So I know that we've already gotten this case, but now we're trying to look for 2-digit possibilities. Let's just write some stuff out. So what are all the pairs, all the numbers that have a digit sum of 9? Okay, and we can actually just test everything out. So what would the product of digits be if 18 was the second number? It would just be 1 times 1 times 1 times 8, which is 8. Similarly here, same product, so 8. Okay, so these don't work. What about this? It would be 2 times 7, which is 14. Okay, so these don't work. 3 times 6 is 18, so these don't work. 4 times 5 is 20, so these don't work. Okay, so that means 11 can't be paired with any 2-digit number, because it forces the second number to be stuff that can't be the product of digits. Okay, maybe let's just try 12 now. 12. Okay, so let's first consider if 12 is the product of digits. Well, 12 can be broken down into its prime factors 3, 2, and 2. Okay, now 12 itself has a factor of, contributes a factor of 1 and 2, which forces this second number to either be 2, 3 or 3, 2. So all we do is check if either of these work. Okay, now what is the product of digits? In both these cases, the product of digits is just 1 times, oh wait, not the product, sorry. The sum of digits in both these cases is just 1 plus 2 plus 2 plus 3, but this is 8, which is equal to neither this nor this. Oh wait. Yeah, okay, so that's not possible. So that means that 12 can't be the product because there is no other number that is a digit sum. So now we go to if 12 is the sum of digits. Okay, well, if that's the case, I already discovered that 9A1 is B0 plus B1, where this was the first digit of the digit sum number. So that means 9 is equal to B0 plus B1. Okay, so again, we can just do all our guessing oops, 3, 4, 5, 6, 7, 8. 7, 6, 5, 4, 3, 2, 1. Okay, so we just need to check if any of these are a valid product of digits. So if this was the other number, then the product of digits would be 1 times 2 times 1 times 8, which is 16. And this one would also be 16. Okay, but 16 is not equal to 18 nor 81. What about this one? We basically get 2 times 2 times 7, which is 28. That's not equal to 27 or 72. Okay, and then 2 times 3 times 6 is 36. Ooh, this is great. Let's check the others just to make sure. So 2 times 4 times 5 is 80, which is neither this nor this. Okay, so it seems 1236 works. Let's check. So is 12 equal to the sum of digits? 1 plus 2 plus 3 plus 6 is indeed 12. What about product? 1 times 2 times 3 times 6 is equal to 36. Okay, so this works. We found another compatible pair. Okay. So I think that, I mean, we've discovered some stuff. Maybe just to illustrate some things that don't work even more. Let's see 14. So 13, I'm going to skip over because we already did a prime example. And so I don't think 13 will illuminate anything else about products. But what about 14? So 14 and a 2-digit number. Okay, now if 14 was the product, okay, then that would mean that 14 is equal to 1 times 4 times something. But 4 is not a factor of 14, or a divisor, sorry. So that doesn't work. So at this point, I'm like, oh, I feel as if arguments are going to repeat. So instead of repeating them every single time, let me just systematically figure out what my possible products are. So possible numbers that are products of digits, because I don't want to have to repeat this type of argument where if the number is a product, oh, it can't be a product, because I feel like I can actually do this all in one go. So for a 2-digit number, sorry, we're looking at 2-digit because we've already looked at all the pairs that have at least one 1-digit number. Okay, so if my number has 2 digits and it's got to be a product, then a few things have to happen. I need xy to divide. So, sorry, if x and y are the digits, I need x multiplied by y to divide my number. So I'm abusing notation a bit here, that when I write xy, I really mean the number itself. Okay, so I think this is already pretty strong, and we can figure out what our possible products are. Okay, so we start from 11, don't we? Okay, now we've already done 11, so I'm not going to consider 11. 12 we've also done, and we realized 12 wouldn't work. Okay, so I'm not going to consider 12 either. Okay, so basically 11 and 12 we've already checked. Now, what's another possible product of digits? Well, let's see if 13 works. Now, is 3, which is 1 times 3, a divisor of 13? No, 1 times 3 is not a divisor of 13. And so 13 doesn't work. What about 14? Does 4 divide 14? No. 15. Does 5 divide 15? Actually, it does. So 15 is possible. Cool. Okay, 16. 6 does not divide 16, so no. 17, 7 doesn't divide 17, no. In fact, we could skip over all primes. Okay, what else? 18, does 8 divide 18? No. Does 9 divide 19? No. Okay, and now the next bit of numbers to check is the ones beginning with 2. Now I'm going to skip over 20 because I know 0 can't be a digit. So how about 21? Now, does 2 divide 21? No. So I can immediately just start checking all of the even numbers, 22, 24, 26, and 28. So does 4 divide 22? Because that's 2 times 2. No, it does not divide 22. So no. Now, does 2 times 4 divide 24? Well, it does actually. So this is possible as far as we know. Does 2 times 6 divide 12? No, sorry, 26. Does 12 divide 26? No, it does not. And finally, does 16 divide 28? No, it does not. Okay. So this is pretty strong already. Okay, what about the numbers starting with 3? Okay, so if I already know that 3 needs to divide my number, I can just check my multiples of 3. So 33, 36, and 39. Okay. Does 9, which is 3 times 3, divide 33? No. Does 18 divide 36? Yes. 3 times 6 does divide 36. Does 27 divide 39? No. Okay, cool. Let's move on. I can start with the 4s. So as you can see, there becomes less and less numbers to check as I move up the number line, because I only need to check 44, 48, and that's all, because these are the only numbers that begin with 4 and have a factor of 4. So if x times y divides xy, that means x divides xy and y divides xy. Anyway, so does 16 divide 44? No, it does not. Does 32 divide 48? No, it does not. Okay, so I'm powering through these. Okay, so 5, the only number to check is 55, because that's the only number that's greater than 50, begins with 5, and is divisible, and has 5 as a divisor. So now I just check, is 25 a divisor of 55? No, it is not. Okay, now let's keep going. 6. Again, 66 is the only number to check here. So you can see it's getting pretty fast now. In fact, these are the only numbers I have left to check. So now for 66, does 36 divide 66? No. Does 49 divide 77? No. 64 divide 88? No. And does 81 divide 99? No. Okay, so we've again narrowed our sample space even more, so there's even less to check. So we know that if a number is a product, then the number is definitely 15, 24, or 36. Okay, so let's just summarize what we know right now. What do we know? We know that for A, B, where A is the sum and B is the product, we know that A, and pretending that we're looking at two-digit pairs, because we have already looked at all of our one-digit possible compatible pairs. Okay, so only looking at two-digit pairs where A and B are both two digits. If A is the sum, A begins with 1 or 2, and if B is a product, then B is either equal to what was possible here, 15, 24, and 36. Okay, so I think that we can just start checking. I think this is small enough. I would be confident in the exam if I had restricted it down to this. So let's just check 15 first, where 15 is the product. Okay, so 15 has prime divisors 3 and 5. So the 5 is already occupied here, which means that the 3 has to go into one of these slots. And so that means that it's either going to be 13 or 31. Now we just need to check, do either of these give us the digit sum? So the digit sum is now 1 plus 1 plus 3 plus 5, which is 10. And that is neither equal to this nor this. And so 15 doesn't work. Okay, so eliminated that case already. Now let's try 24. 24. Now 24 has divisors, it's 6 times 4, which is 2, 2. Well, 2 and 4 have to be divisors, right? 2 times 4, which leaves 3. And so because the 2 and the 4 have been taken up here, that means the 3 has to go into one of these slots. And again, we get either 13 or 31 as our digit sum. But then our digit sum is then 1 plus 3 plus 2 plus 4. And this is equal to, again, 10. And that is not equal to this or this. So 24 doesn't work. Okay, so this is already getting really quick. We didn't even have to do that digit sum stuff. So 36. 36. Well, we already did find 12 and 36, didn't we? But let's see if there's any other possibilities. 36. So if we just had another number, 36. 36 can be broken down into 6 by 6, which is 3. Oh, well, we have to have 3 times 6. And that leaves how much left? That leaves 2 left, which means it's either going to be 21 or 12. And only one of these is the right answer. And we already saw that the answer was 12. Okay, so we've ticked this off. Okay, but there are no other possibilities for the product number, which means that essentially we've checked every single possible pair. And that means that our final answer is just the 2 that we found. The CPs are 9 and 11. Oh, sorry, I'll write it in order. 11 was the sum, 9 was the product, and 12 was the sum, 36 was the product. Okay, so this is our final answer. And you can see that we actually checked everything. I think that the product stuff here was the best way to narrow this down, actually. Okay, now let's just real quickly, if people want to leave, they can go, but let's just real quickly look at the AMT solution just to give you ideas as to how you might think about this if you didn't want to think about it in a very hands-on way. Like some people are very comfortable working with algebra and equation bashes, but I think that also, there's also a risk of you sort of getting lost, and well, it depends on you. It's a matter of preference. Okay, so they presented two different methods in the AMT solutions. The first method was somewhat similar to what we did, which broke down the problem into cases. So case one was when the product, which we're going to call P, and the sum were both, oh no, I think case one was just when the product was one digit. And then they reasoned with that. But as you can see, like it took a little bit of work to even realize that this was a case worth considering. And we sort of did some examples to find out that it was a case worth considering. And we already saw what happened with that. And case two was when the sum was one digit. And again, oh, sorry, no. So this is the one that we started off with. And so these two cases are reasoned with quite quickly, and there are only a couple possibilities. And then this is the long bit, as we already realized, because we very quickly discarded of the one digit case in sort of one go. And then at this point, it was sort of just an equation bash. And so they got the same equations. But again, as you can see, it took us a little bit of work to be inspired enough to write it this way. And we were inspired to write it this way because we saw that the one digit case didn't work for a very particular reason, which was that the single digit already occupied too much of the digit sum. And yeah, a lot of algebraic manipulation. And the second method was even more straight up algebraic manipulation, like no cases involved at all. So yeah, I don't know if people want to read through this, then go for it. You've got the whiteboard link, right? Okay, I have no idea what happened in the chat. Okay, so do people have any questions? No questions. I saw that very quickly amidst all of the whatever face this is. Okay, nice to know you were all paying a lot of attention during that one. Anyway, yeah. So as you can see, this wasn't actually too bad, and you might have been put off at the beginning just from the sheer magnitude of all the possibilities. But once you find some rules and restrictions, it becomes a matter of just checking a few things. But by finding rules and restrictions, you've essentially checked all possibilities. So it's not too bad. I think question 8 felt harder than this one.